almost at the end of this thing. Looks like we might make it after all. It got dark there for a little bit. I didn't know for sure if I was going to make it all the way through, but we've got 8 left. We could do this. All right. So, where are we at? Subarray sum equals K. Got a link in the description. Given an array of integers and an integer K, you need to find the total number of continuous subarrays whose sum equals to K. This sounds like one that we did already, which was the longest consecutive subarray. And that's the one where I spent a whole bunch of time trying to do a tree. And what did I end up doing instead? I don't remember that problem anymore. That's unfortunate because I think this one's really similar. Maybe I'll remember. Longest contiguous subarray. Oh, I remember now. Longest contiguous. Hey, how's it going, Abdul? Hope you're doing good. Did you do this one already? It's like really late for you, so hopefully yes. Yeah, so this is the problem that reminded me of the longest continuous subarray, and that was the one where we kind of added things up and basically looked for when the integers would match, because we would know then that we had a span that what you call it, went all the way up and down, and that was good. That worked out really well. So we basically had a clever solution there. So I don't think that problem would particularly help us there. Help us here. In this case, we need to find the total number of continuous subarrays whose sum equals to K. So in this case, we've got 2 as the input. So we can see here that 1 and 1 equals 2. And also 1 and 1 equals 2. So we've got our output of 2. 14 hours ago. Holy cow. Yeah, I'm running late tonight. So the length of the array is the range 1 in 20,000. That's a big array. The range of numbers is -1,000. So we do have negative numbers, 2,000. And the range of the integer K is, exponent 7. All right. 0%. Awesome. All right. So first thoughts. Given an array and an integer, well, there's definitely no way that we can not look at every number. So at a minimum, we're going to have to touch every number once. This is fine. This is a really boring example. Well, I'm kind of thinking about the approach I kind of started thinking about with the other problem. And, you know, it's kind of like a bit of theme here. Whenever we have an array, like running sum seems to factor in. So I'm kind of thinking about it that way. So what if we were to just go through and start summing numbers? Ooh, definitely not doing this in C, by the way. Nope, nope. So that's our input. And if we did a running sum, when basically we would do 1 plus 1, that's equal to 2. Plus 1 is equal to 3. It's not our target. Well, I'm kind of thinking about it's like we could also kind of subtract 1 to get back to 2. That doesn't really help us though. I'd have to subtract this one in order to get 2 to kind of see that array. So that was kind of interesting. I did 3 operations though for 2 input, so we're probably looking at like a n log n or even n squared solution there. So let's take a look at a bigger example. If we did, let's say our target was, I don't know, 3. So 1 plus 2 is 3. Plus 3 6. I don't like how this is going. Plus 4, 10. Plus 5 is 15. I was kind of thinking about basically kind of minusing items off now that we've reached the end. Like, okay, 14, 12, yeah, 15. Oh wait, I'm minusing. 9, 1, and then yeah, that's it. So I don't know, that's kind of weird. I don't know that it really helps us any. You know, kind of wonder if I know my target, I'm wondering if I can kind of do some shortcuts here. But I can have negative numbers, so I don't think I can be greedy and just stop early, because the next number might put me too high, but then the one after that could bring me back down again. So I think I still have to do all the math that way. I mean, I would like to use memoization. So what if we just had a big hash? A running sum. Okay. So it's almost like, you know, we had a range 0 to 1. In this case, it would be equal to 3. 0 to 2 is going to be equal to 5. And then I could subtract 1 to get 1 to 2, which is going to be, I always want to add these numbers. So that was 6, and this is 5. And then from here, I could basically add the next number to both of these, which is interesting. Huh. Yeah, I don't hate this so far. I'm gonna write this out a little bit differently though. So, what if I had an array, and this array keeps track of all the math that I've done so far. So if my target is 3, let's do a bigger one. Let's just say 5, sure. Then I would add 1 plus 2, so I get 3. Well, first I guess I gotta keep 1. Then I'm gonna add 2. So what I'll do is add 2 to this number, and also add 2 by itself. I think that's okay. Next I'll add a 3. That makes this a 6, this a 5, and I'll add a 3. And here I've got my target, so I'm going to count 1. Alright, now we're going to add a 4. We got 10, 9, 7, and 4. And then finally we'll add 5. This is 15, 14, 12, 9, and 5. So we see a 5, so that would be a second. So I don't know, that didn't feel awful. Did I do this right? I expected to see a 2 and a 3 here, but I might have just... Was that the first 5 I saw? Yeah, I think so. I think that's the only... Yeah, I think I got the right answer there. So what was the runtime of that solution? I did... Every time I looked at a new number, I would have to go back and add that number. Is it n times? The correct answer is 3. Uh-oh, did I do it wrong? So we got 1 here. 1 here. Where's the other 5? That's the only 5 I see. I'll just walk through it again. So we said 1. Okay. So I'm going to keep track of the number of additions we did too. Additions. So far I wrote 1. And then we're going to add 2. That's 3. We're going to add, and that's going to be a total of 3. Then we add in a 3. So this becomes 6, 5. So count goes up to 1. And then 3. We get a 4, 10, 9, and 7. And then 4. And then 5 is going to be 15, 14, 12, 9, 5. And I forgot to count it up. Yeah, and if they didn't have numbers, if they didn't have negative numbers, we could really optimize this, but those negative numbers mess us up. So for the, I can just add this up. So for how many calculations I did for an array of size 5, I did 1 plus 2 plus 3 plus 4 plus 5, which is, it's n factorial, isn't it? So that is probably too slow. Is that true? What math was I doing that was duplicate? What did I not need to do? 1. 3 plus 2. The memory complexity there was n, because I did have to keep kind of track, which is interesting now that I think about it. What if I did it all in line? Like if this is my input, and I would start with this, and I could take and add 1 to every one of these. So it's like first pass, I would just say, are you it? 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 Yes, count 1. Then I would take this one and add, are you it? Are you it? Are you it? Are you it? Start here. And this time I would add whatever this previously was. Yeah, so I need to know what it previously was. This is just a different way of representing the same thing. Are you it? 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 Wait, I'm getting wrong. I'm getting all mixed up here. Let me try that again. So I'll start with array. I see the first value. Then it's conceptually, I can say 1 and 1's the rest of the way. Then when I get to 2, I need to leave this here. Is that right? No, that's not right. Yeah, this way doesn't make sense. I like the way I had it before better. So I start with 1. When I add the 2, I can increment it. Add the 2. Add the 3. 6, 5, 3. Add the 4. And then we get the 5. And then 5. Yeah, I mean, I kind of forget what the curve looks like. I'll look at big O curves and see how n factorial fits in there. I think it's better than n squared, isn't it? I don't know. My math is weak. It's been too long since I've had to think like this. N factorial is the blue line. Oh, maybe I'm not thinking factorial. No. Factorial is n times n minus 1 times n minus 2 times. What do you call it when you add them up together? The summation? Why am I brain dead? Because basically it's kind of like n squared, except that n gets smaller every time, so it's better than n squared, but it's not as good as certainly linear. And it's not as good as n log n. I think it's going to be good enough. Let's just try it. It seems like this is going to be an easy thing to program, so I'm sure it's not optimum, but it seems kind of fun. So first, let's declare an array. Let's cache equals new array of size nums.length. If I know the length of an array in JavaScript, I like to go ahead and just allocate it. It's micro optimization, but sure. Nums.length I++, right? And what we'll do, I should probably initialize that to zeros. I don't know. Think about it a little bit. So what was I doing here on the, look at this simple example where we've got 3 ones. I want to say cache at I look at each element. Running sum array went from there. Kind of like the products array you did for the, yeah, that's the products one I was kind of thinking of. Yeah, so I thought about the running sum, but I couldn't, I felt like I had to do some subtraction there and I was getting tripped up. So if I did running sum, then 1 plus 1 plus 1 is 2. Plus 1 is 3. But then what I wanted to do is basically go back and kind of subtract this 1 to make sure I looked at all combinations. So it's like I'd have to subtract the 1 from both of these, which would make this a 1 and a 2, and then I could do the same thing here. So let's try that with a bigger array, see what that looks like. And we'll say target is 5 again. There should be 2 of them. Clean up a little bit. So we start with 1. Our running sum then is going to be 3, 6, 10, 15. Then we minus 1 from all of them to 5. So we got 1. 9, 14. Then we take the 2 back. 3, 7, 12, get rid of the 3, 4, and 5. So there's our second one. Then get rid of the 4, and we're back down to 1. If you have the beginning and end indices of a subarray, using the running sum, you can get that subarray sum. Yes. So I understand that. Beginning and end, and I can return the running sum. But I just don't know how to avoid that kind of pyramid where I have to back the numbers out. So I look at this subarray. Then I also have to look at this subarray and this one. That's just where I get tripped up. I don't understand how to back it out. Here's one way to step it up. Just start like that. And so we say cache.push nums at I. And then for let j equals so I plus 1. Let j equals, yeah, actually let's do that after. Okay, cool. So for j equals 0, j is less than cache.length j plus plus. And then we'll loop through the cache and we will add so cache at j equals cache at j, whatever we got there, plus nums at I. And then when we're done, we will add cache or nums at I there. All right, then we also need to keep our count equals 0. And every time we do this, we need to say if cache at j equals target, which is k, then count plus plus. And then down here, we can also say if nums at I equals k, count plus plus, return count. I think that's it. It's not optimum. There's no running sum going on there. We have 4 hints too. 4 is a lot of hints. That makes me think that I'm oversimplifying. So I got the right answer there. What about, try the 5 example. And we're looking for 5s, sure. Come on, okay, that's good. If I'm looking for 3s, there should be 2. Okay, what about like a negative 1? I should get a 0. What if I did a bunch of 1s? And I said I wanted a 3 or something, just trying some random tests. Alright, I mean, I think it's pretty good. Let's give it a shot. Hey, that ended up being okay. That ran faster than I expected too. Oh, but yeah, not super great runtime. Looks like there's a pack of us in the middle that did the same kind of thing. I do like that this one only took me 20 minutes, so I'm happy. Not that I don't like challenging problems, but it's just like this is day 22 of doing this, you know, so it kind of wears on me a bit. So this looks like what you're talking about, Abdul. They keep a sum. They initialize a map. Okay. They add up, so they increment the sum, running sum. Oh, interesting. If the map has the sum minus k, then the count increases. Wow, that's interesting. Yeah. Was this an easy problem? If map has the sum, then set the sum equal to the map, get the sum plus 1, otherwise we initialize it to 1. So that's interesting. So whenever the map has our sum minus the number, that's really interesting. I'm still trying to figure out exactly what that means. So we do a running sum. Okay. And if the map has my sum minus the K, I'm going to have to look at this. Let's see here. So in the simple example, we got 1, 1, 1. They say run through 1 and keep a running sum. We're looking for 2's. So in this case, our map does not contain 1 minus 2. It's negative 1. So what do we do? So that was false. If the map has the sum, it doesn't. Otherwise, set it to 1. Okay, so our map becomes 1 with a value of 1. Okay, we come back around. Now our sum becomes, 2. 2 minus 2 equals 0, which is not an array. So now let's go ahead and set map at 2 equal to 1. Okay. Now we add that third one, and this is where the magic happens. Oh, hint 4, okay. 3 minus 2 becomes 1. Okay. So we return map at 1 plus whatever our current count is, which was 0. So I must have goofed something up. Oh yeah, they initialized a 0 and 1. Okay, yeah, so let me try that again. They initialize a 0 with a count of 1. Alright, sorry about that. Okay, so running sum is 1. 1 is not in the list, so we keep track of 1. We add it up again, we get a 2. 2 minus 2 is 0. Boom, so our count goes up to 1. Because we've seen a 2. Okay, and that's our answer. That makes sense to me. Okay, and then in addition to that, we also cache it. So we say 2 has a value of 1. All right. Now our running sum is 3. 3 minus 2 is 1. Okay, which exists. So we're going to have to add this to our count too. So that's how it gets the right answer, but I'm still having a kind of hard time kind of internalizing it. But oh, you know what it is? So the thing I talked about, like the step ladder, where I would kind of like do the math and then do less math and then do even more. I'm doing, you can see like this item is like the 5 is in every column. Like I kept it around for too long. What they're doing instead is, instead of doing this kind of step ladder thing, they are minusing K. So they only do like the addition for the items where the sum minus the target we're looking for has been seen before. So it's kind of like, instead of subtracting and backing out these numbers, which is what I was kind of thinking, they're subtracting the K and seeing if that number has existed in our as a subarray before. So I still like don't fully grok it, but I think that's kind of like the trick there. That's how they reduce the triangle. Now let's go look at those hints. That is slick. All right. I like that solution though. Not the greatest, but it was a good one. So hint 1, will brute force work? Maybe. These numbers were pretty big though. 20,000 array is nothing to sniff at. Can we optimize it by using some extra space? I did. What about storing some frequencies in a hash table? Okay, yeah, and so that's essentially what we did. So it's so interesting. So we took the sum minus k and saw if we had a subarray that was in there. So it would be our running sum minus the target is equal to a subarray. So it's like kind of saying like, is there a subarray in there that exists that's the size I need it to be? Brute force does work. Awesome. Hint 4. Sum at I and j, two numbers, is equal to sum of 0 and j. So from the beginning to j minus O and I, which is the beginning to I, where sum of I to j represents the sum of all elements from I to j1. Can we use this property to optimize? Oh man, you're chat cheating on me? Broke my heart. It's all good. Let's see here. So sum ij. This seems like an important property that would help for help with other problems. So what is it really saying? This also makes me wonder if there are other like math theorems that I should probably revisit because I haven't thought about them in a long time. But sum of any two numbers is equal to the sum from 0 to that number, the second number, minus the sum of 0 to the first. So if we have a 1, 2, 3, 4, 5, and I'm going to just pick two numbers, 2 and the 5. It's all good. We're saying the sum of 0 to 2, no, 0 to j, 0 to 5, minus sum of, I should use indexes here, not the actual numbers, so this is what I was actually thinking. So the sum of 0, 4 minus the sum of 0 to 1. Sum of 0 to 4 is, well, I'll do this one first. 0 to 1 is 3. And then 6, 10, and 15. So 15 minus 3 is 12. So we're saying the sum from 1 to 4 is 12. So if we add these three numbers up, if I did it right, which is not guaranteed, 3, 6, 10, 15, and sum from 0 to 1 is 3. So they're saying the sum is 12. So it looks like I did something wrong here. But I think this is basically that kind of thing I was alluding to, where basically instead of doing that stepladder thing where I said I would have to subtract the 1, and subtract the 2, subtract the 3, subtract the 4, they're saying because of this property, all we have to do is just see if this equals our target. So we could take our sum minus our target. So sum at I and j is equal to our sum minus our target. I don't know. I'm getting confused. I'm fine with this. Alright, cool. Well, I'm happy with that. And I hope the rest of the couple of days are a breeze here. I'll tell you, to be honest, I'm looking forward to having a little bit more freedom. There's some weaknesses I've kind of fallen into while doing these problems, and so I'd like to kind of work on things I'm particularly weak at, like those dynamic problems. So I think I saved a bookmark of, I don't know how to show my bookmark bar. Maybe I did it in Chrome or something, but oh no, there they are. I found a list of top 20 dynamic problems, so I was kind of thinking about trying to work through these, and I'm hoping that they kind of work up from easier to hard. And I think if I did 20 dynamic problems back to back to back to back, that I would be better at doing dynamic problems. So that's the hope. So that's what I'm kind of thinking about doing next after this 30-day challenge is up. So yeah, that should be cool. And I'm going to watch and read some stuff about that in the meantime. So should be good. All right. Well, thanks for hanging out. Hope you have a good night, or it's getting to be about day for you, Abdul. So good luck with that. Whew. I cannot do that. All right. Have